Hello, in this second video on counter sets, we stick to the one dimension, but add a little bit of more geometry to these sets. A quick recall that the standard construction of a counter set starts with, say, the interval 0, 1, and in the next stage you are left with two intervals that are lambda length. And then if you take lambda to be kind of a percentage of what proportion of previous intervals are left. So here, these two intervals will in turn be divided, not divided, but we remove a middle interval so that the remaining intervals are lambda times the length of previous one. So here they will be lambda squared, each one, and you keep going, and the intersection of unions of these intervals will be a counter set, which of course depends on lambda. We saw that the Hausdorff dimension of this set is log 2 over log of 1 over lambda. And this lambda can be any number between 1/2 and 0. Okay, the twist, the new addition will be that now we require that as we move on, we replace lambda with a new lambda k. So why keep the same proportion if we can just play around with it? So the way it starts is that we have a sequence, lambda 1, lambda 2, and so on. So let this be a sequence of values in 0 and 1/2, the same as here. And then we construct a counter set, which now depends on the sequence. So previously C lambda is kind of C of t, where t is the constant sequence lambda. Similarly to C lambda, except that so we can intervals at level k are lambda k times, so we have to say the length of the intervals. At this, the length of intervals at previous generation k minus 1 level. And if you follow the construction, you will see that I add these just so that you can verify whether you're thinking in the same terms as I am here. So there is no further gymnastics here, just the same number of divisions except for this length. So at a stage k, we will have 2 to the power k, because every interval gave 2, and we did this k many times. So we will have these many intervals of each of length. Okay, let's see. You started with the unit interval, then you multiplied by lambda 1, and the next generation have length this much, so this will be like that value, which we denote by SK. Again, I'm following the book by Mattila, and this is section 411. Okay. Here comes an interesting moment where it would be really beneficial if you knew of Hausdorff measures with gauge functions other than the power. So the way we defined Hausdorff measure was you cover a set by union of sets, and then you take diameter to power s, and then you do summation over I, and then you infimize overall coverings at delta cap diameter, and then you then take limit as delta goes to 0. That's how you construct Hausdorff measure of a set. But there's a generalization which says, okay, here you can see that this is a function of diameter of a set, and then you can say, well, why not define these objects with any function other than this diameter to power s. So here you're looking at the function ht being t to power s, and so you evaluate h of diameter, so this becomes h of the diameter. So this becomes the function h applied to the diameter of this ei, and not to power s, that's the function h. And then you take again infimum overall coverings at delta level, and then you let delta go to 0. And then this becomes a Hausdorff measure with respect to this function h. So if we follow this notation, this is really h of t to power s. But because these functions are completely determined by this fixed number s, that's why we write h as h1, h2, h3. But again, we don't have to confine ourselves to only powers of diameter. We can work with any function of this. Well, not technically any function, but so here we're having a new definition for a generalized Hausdorff measure. And we can do this whenever you have a function defined on non-negative values, because we apply it to diameter, so we only need to evaluate it on positive, non-negative numbers. So, and if we don't want to deal with crazy stuff, we can assume it's continuous and it's increasing, which, well, if it's not increasing, then there is no point in saying you cover by diameters delta and you let delta go to 0, because if your function is arbitrary, you don't know if it does anything with forcing diameters to go to 0. So that's where this increasing comes from. And something I'm not sure about is if we always assume that this actually equals to 0. I think if it's not 0, then this measure is actually not that useful. Probably it produces infinity for a big deal of sets. Maybe it's infinite for any non-finite set, but I'm not sure. But anyway, you can define Hausdorff measure with respect to any such function, and the Hausdorff measures in the more standard, more common form are nothing but with this definition applied to h being just a power of diameter. Okay. Well, for terminology, you can, if you want to search about these and read more about these, they are called a gauge function. So we say the Hausdorff measure with the gauge function h. And these are quite useful. Sometimes just a being a real number, are not enough to distinguish sets. So sometimes you need to move into these gauged Hausdorff measures to really be able to tell one set from another, to tell that this set is bigger than that, because none of these captures them. They agree on the value of H alpha, HA measure, if A is the integer. So we get to refine things, and you will see an example when we go back to discussing the Hausdorff dimension of these generalized Cantor sets constructed through this sequence of lambdas. Okay. Hope that is a crash course in generalized Hausdorff measure is sufficient to give you some idea of what we're talking about here. So what is the relevance to the construction from above? So remember we had a sequence of lambdas, lambda 1, lambda 2, and so on. And then to that we associated a counter set T. Now the relevance of this gauge functions is that if H is a continuous and increasing function as above from 0 infinity to 0 infinity, if H is a gauge function for short, and this H of lambda 1 times lambda 2 lambda k equals 2 to a negative k. So suppose, so I'm not saying that this is true, suppose there is some increasing and continuous function H such that this unique identity holds for every k. Then this Hausdorff measure with respect to this gauge function of the counter set C T is less than or equal to 1. Remember that these were easy to get because the steps of the construction provide the coverings you need, and if you need a delta covering you can move into later and later stages of the construction so that the length of each interval will be less than delta, so it will be delta covering. So this will be less than 1, and as we saw in the previous video, it's often more delicate to get the lower bounds. Just showing that the lower bound is positive is a big deal. Okay, so that can be regarded as a theorem, in fact. So it's probably the main claim in this video, that if for these choices of lambda you have such an increasing function, then the Hausdorff measure constructed with respect to that will have positive and finite measure. In a sense, this H will be the correct dimension, although it's not a number, it's a function, the correct measure, let's say, for sizing these CTs. Okay, and then there is a converse to that, which can be regarded as our second one. It says that if you start with H, remember above we started with lambdas and then we said if there is such an H, but the nice fact is that starting with a continuous and increasing H, that moreover satisfies this doubling condition, that H of 2R is less than 2 times h of r. So it's a function that grows. It's an increasing function, remember, but it's not like crazy increasing. So if you are here and here, the value of the function at 2r is not more than twice the value at r. So there's kind of a cap on how this function h grows. So suppose we have now start with this continuous increasing function with this property. Then we can select lambda k inductively. So remember, these in particular are supposed to be here, such that this equality star holds. Let me recall what star was, that h of lambda 1 multiplied until lambda k is equal to 2 to negative k for every k. So this, of course, needs some calculation and thinking, but it's not any shocking claim. This condition is needed exactly to be able to select these lambda k's in this range. Okay, and then we can construct a counter set. Now this counter set, we can say, depends on the gauge function h, right? Because ultimately it depends. So this depends on lambda k's, but lambda k's ultimately are almost uniquely determined by h. So we can say to every, if you start with an increasing continuous function with this doubling inequality, then you can construct a counter set that corresponds to it. Okay. But based on the previous claim that we had, the Hausdorff measure of this set computed with this gauge function h itself is finite and positive. Okay, so this became a little bit too abstract, but then comes the nice examples. Let's take h to be this function. It's this, so this would be this would give us the s-dimensional Hausdorff measure, but then we multiply by this value. Remember that the gauge functions actually only when r is close to 0 count, because the diameter of the coverings are forced to go down, and when so parentheses, notice for r small near 0, this is bigger than r to power s, because you multiply by this number, which actually goes to infinity. But because log is very, very small, smaller than any polynomial, so it's at the same time smaller than r to power s minus epsilon for every epsilon positive. So here I must say that s is less than 1. And bigger than or equal to 0. Let me double check that so this goes back to the point that it's equality here allowed. Yeah, of course, we don't want this to blow up and go to infinity. If s is allowed to be 0, it goes to infinity, so s has to be strictly positive. Okay, so here so notice that r to power, say, 0.3 minus epsilon is a larger quantity than r to power 0.3 because you are talking about range of very close to 0, and these functions look like this. And the smaller, so this will be r to power 1, and this is probably r to 0.5, and r to 0.3 is larger, so the smaller the power, you get bigger values. So this gauge function you can say that it's something squeezed between r to power s and every r to power s minus epsilon. So this is bigger than r to power s, but also it's not big enough to hit any other power. And that's exactly why this becomes a very delicate thing. If you compute, so what this example tells us, so from this, let me call this formula 1. So from 1, you actually conclude that if you computed the usual Hausdorff measure with h to power s of this set, then you would get 0. Okay, so h here is larger, so if you put a smaller gauge function, then if it's positive for a bigger gauge function, then it's 0 for the smaller one. So here I'm comparing to r to power s. I'm comparing it to that. It's a bit crazy, but compare this situation that if you know that h2 is positive, then it implies that h 2 plus epsilon of that set is 0. And it also means that h2 2 minus s of that set is infinity. That's by definition what Hausdorff dimension is. So in the usual Hausdorff dimension case, this is what happens. So here we see that the set we're looking at is not s-dimensional. I mean, it is s-dimensional in fact, but it doesn't have positive s-dimension. So dimension of CS is actually equal to s, but it doesn't have a positive measure. And if you change your s value, you either hit 0 or infinity. So the formula 1 is saying that to capture for exactly what measure you get anything positive, you have to move into this gauge function. Okay. There's a similar example with h of r equal r to power s. Now this time you divide by log of 1 over r, so you go in the other direction. And in this case you get a set, so here s can be 0, but not 1. Then dimension of this counter set you construct is again equal to s, but this time you get that S-dimensional measure of CH is infinity. So compare this to this. This time you're on the other side, that HS, although it's S-dimensional, in the first example you had 0, but now you have infinity. And not only that, it's not even sigma finite. That means even if you look at pieces of this counter set, again HS measure is going to be infinity. So it's like it's truly very large from the point of view of S-dimensional Hausdorff measure. And the only way to see finite measure again is going into the right gauge function. So this may have been a bit too much if you weren't familiar with generalized Hausdorff measure, but then there are some corollaries that you can appreciate even if you're not at all familiar with the generalized Hausdorff measure. If you take extreme values, extreme cases of s equal 1 in example 1 and s equals 0 in example 2, then you get respectively. So in the first case, what you get is a counter set of Hausdorff dimension 1, which is equal to S, but a 0 Lebesgue measure. Well, I must say, I never mentioned this outright, but any counter construction of the types we've considered will end up with sets that have no L1 measure, Lebesgue measure. That can be C, for example, from Lebesgue differentiation theorem, which says that if you have a set of positive measures, then there's a point in the set whose neighborhood has almost full measure. But we know that it never happens with counter set because you always remove a proportion, a minimal proportion of that set. If you're not familiar with that, then probably you need to calculate by hand to see that their measure is 0. And what happens in the other extreme case of s equals 0, then you get a counter set of Hausdorff dimension 0. So sets of Hausdorff dimension 0 are empty set, finite sets, countable sets. But now we have a set that is uncountable because all counter sets are uncountable. We talked about it in the previous video. So maybe these are the examples you will remember from this video, that you can have a set with full dimension. It competes with the interval in dimension. It has Hausdorff dimension 1, but it has 0 Lebesgue measure. So that's it. Such sets exist. On the other hand, you can sets of 0 Hausdorff dimension that are nonetheless quite big in cardinality. Okay, so I think that will bring us to almost the end of this video. Let me review this real quick. So these are quite flexible constructions you can, and people have, of course, considered further variation of these. One nice question I saw on Stack Exchange was, what happens if in the construction of counter set, you don't insist on this being right in the middle? What if you shift your intervals? Maybe this interval you just move towards this other one, as long as you don't get any overlap. And maybe here you move this toward that. Does it matter for the dimension of the set that you end up with if you have these gaps differently distributed? And that's a question you can think about. Then if you're really curious, go to Stack Exchange and find the answer. So in next video, I'll probably talk about fat Cantor sets, and those are another nice phenomenon. Until then, have a nice one, and thank you for being with me today as well.